In this exercise, we'll review some basic properties of matrix multiplication with an eye toward a few things that are going to be useful for us later on in the semester as we think more deeply about how matrices work. If you're following along in this video in Edpuzzle, respond to the prompts as they arise. The first portion of this activity, taken out of Austin's Understanding Linear Algebra online text, asked you to form the matrix product of this matrix with that matrix. So the first question I have is, what is the dimension of this product going to be? First of all, what is the dimension of the first matrix in this product, one that I've underlined? That matrix has 3 rows, 1, 2, and 3, and 4 columns, 1, 2, 3, and 4. So we'll call it a 3 by 4 matrix. How about the matrix which is multiplying on its right? That matrix is a 4 by 1. It has 4 rows, but only a single column. Often we will call that a column vector if we're feeling like giving it a different name. We can really just treat it like it's any other matrix, though, in this problem. So are the dimensions of these two matrices compatible to even form that product in the first place? Will we get a reasonable answer? In this case, the answer is yes, because the number of columns in my first matrix and the number of rows in my second matrix in this product match. They're both 4. So it's possible for me to form this product at all, because the number of columns in the first matrix matches the number of rows in the second. Now that I know that this is possible, what do I expect the dimensions of my product, the result, to be? Well, the product is going to have as many rows as the first matrix has, and as many columns as the second matrix has. Therefore, my product of these two matrices is going to have 3 rows and 1 column. These are things I should always try to figure out in advance before I try multiplying matrices, just so that I know what the shape of my finished product matrix will look like. I know now that to form this product, I'm just going to need to find these 3 entries. Well, how do I find these 3 entries? Where am I going to get the first entry in this product matrix from? That first entry is going to be a result of taking the first row in my first matrix, and the first, in fact, the only column in my second matrix, and forming what sometimes we'll call the dot product of those 2 vectors. The way to think about what that means is that we're really just adding the pairwise products of the entries in that row and that column. So for instance, the first entry is going to be 1 times 3 plus 2 times 1 plus 0 times -1 plus -1 times 1. The second entry will be 2 times 3 plus 4 times 1 plus -3 times -1 plus -2 times 1. So you're tracing your finger across each row and down each column to form each of these dot products. And what I get is the answer for 11, -10. So that's the basics on how to multiply matrices. Let's take that a little bit further and look at part B. Suppose now that A is this matrix shown right here. If X is a vector such that A times X is defined, in other words, if it makes sense at all for me to form that product, then what does that tell me about the dimension of the vector X, and what does that tell me about the dimension of the product A times X? First of all, what can we say about the number of rows in the vector X if this product makes sense at all? The number of rows in this vector has to be the same as the number of columns from the matrix which is multiplying it on the left. Since that matrix has 3 columns in it, that means that the vector that I place here has to have 3 rows. And now that this product actually makes sense, the dimension of A times X, just as in the first example, is going to be 4 by 1, because it will have as many rows as the first matrix and as many columns as the second matrix in that product. Taking it a little further, in part C, suppose that I have a vector all of whose entries are 0. If I take any matrix at all and I multiply by that 0 vector, what do you think the result is going to be? So any old matrix A, multiply it by a vector all of whose entries are 0. What's the result? Well, the result, as you might expect, is going to be a vector, all of whose entries are equal to 0. Why? because every one of the entries in this product is going to be the result of adding the products of some row of A with the column of all zeros. And 0 times anything plus 0 times anything plus 0 times anything, and so on and so on and so on, is always going to give me a sum of zeros, which turns out to just be 0. So A times the 0 vector is always going to give me the 0 vector. All right, what about multiplying A by some other types of vectors? What can we say in general about the product of a matrix times a vector that can help us generalize a little bit more? So suppose now, in part D, that I have a matrix and its columns are the vectors whose names are v1, v2, up through vn. And suppose that I take the vector that I call e1, sometimes called the first standard vector. This is the vector whose first entry, that's where this 1 comes from, the first entry here is 1, and all the other entries in this vector are 0. So what do you think is going to happen if I multiply my matrix A by this vector? Let's start by looking at a specific, concrete example. Suppose I have this 3 by 3 matrix, and this is my A, 1, 2, 3, 1, 4, 9, 1, 8, 27. If I multiply that matrix by 1, 0, 0, what are the entries in that product going to be? Well, when that product happens, I'm going to take the rows of my matrix, multiply them term-wise by the column that I have over here, and add those results. But notice which of the entries over here are going to get multiplied by the zeros, and which of the entries over here are going to get multiplied by that 1 in my vector. That 1 is going to end up multiplying this entry, and that entry, and the zeros are going to end up multiplying everything else. So that when I add those products to one another, the only thing that's going to survive are the entries in that first column. And as you might expect, this is not an accident. This is something that was not special to the matrix that I wrote here. We can imagine that any matrix that I put here in front of this first standard vector is going to give me the same result, because this 1 in the first entry is always going to multiply the entries in the first column, and the zeros that round out my vector are going to multiply everything else. So that when all of the dust settles, what do you think the product of A times E1 is going to be for a generic matrix A, whose columns are v1 up through vn? That's right, this product is going to exactly be the first column of the matrix A. In other words, the vector v1. This is actually a really handy tool as we go further into the semester. This gives us a way of recovering via matrix multiplication one of the columns of the matrix A. If I want to pull the first column out of my matrix A, all I have to do is multiply that matrix by this first standard vector. As you might expect, multiplying by the second standard vector, where the 1 goes into this entry instead of that one, so it's 0, 1, and then the rest are all zeros, that's going to give me the second column if I multiply on the right, multiply on the left by the matrix A, and so forth. So this nifty little multiplication can pull out, it can extract any column of a matrix that we wish it to. All we have to do is multiply that matrix by the respective standard vector. Finally, let's take a look at part E. Suppose for the moment that I have this 2 by 2 matrix, 1, 2, negative 1, 1, and this 2 by 1 vector, 6, 0. The question asks, does there exist a vector x such that A multiplied by that vector x gives me B? Well, we need to turn that question from a vector question into an equations question that we could have answered in chapter 1. The way that we'll do that is by taking the vector x and rewriting it in its components x and y. If I then form the product A times this x, what are the entries of A times x going to look like? They're just going to be x plus 2y and minus x plus y, respectively. And so, if I want to know whether there is a vector x such that ax is equal to b, what I'm really asking is, are there values of x and y such that x plus 2y is equal to 6, 6 coming from my b, minus x plus y equal to 0, again coming from my b. And because this is an equation of two vectors, the components of those vectors therefore must be equal to one another. So what I'm really asking is there an x and a y such that x plus 2y is equal to 6 and also minus x plus y is equal to 0? That's a system of two linear equations and two unknowns, for which all I need to do is make my augmented matrix and perform row reduction. When I perform the row reduction on this, how many pivots do I end up with? A couple of operations later, we find out that this matrix has 2 pivots, one in each row. In other words, what are my basic variables? My basic variables are x and y, and I don't have any free variables. Therefore, the values of x and y are determined specifically by the system itself. And in fact, we can read off from this solution, x is equal to 2, y is equal to 2. So is there a vector such that a times x is equal to b? Yeah, specifically the vector 2, 2. So we have a system which is consistent. And because the system is consistent, there exists a solution to ax equals b. We knew that because there were a full set of pivots for this system of equations that we got from multiplying a times x and setting it equal to b.